There we go. Now I'm set up. All right. I'm going to be talking about microservices. Who's heard of microservices? Nobody? One? Yeah, we've been talking about this for about 3 years. How many people, I think we've asked this a couple times, but I'm hoping you'll be more energetic right now. How many people are doing microservices? Just a couple. How many people have been told they're going to do microservices? More people? Okay. All right. My name is Christian Posta. I'm a chief architect at Red Hat. I wrote the book, Microservices for Java Developers, of which we do have printed copies. I have one here myself. If you fill out the survey and return it to the check-in desk back there, then you too can have a printed copy. I'm a contributor to a bunch of open source communities. I'm a committer on things like Apache Camel, ActiveMQ. I'm a contributor at times to Apache Kafka and others. But I did spend about a year at Zappos.com. This was about 5 years ago. And I was involved in what we're now calling monolith to microservices approach, where their whole website, the front end, the administrative end, some of their derivative websites like 6pm.com and those, were all run by this monolith. When we talk about monolith, this was a monolith. This was written in Perl. And Bash scripts in Perl. And they felt the crunch that they weren't able to keep up. They weren't able to compete with some of these boutique startups that were challenging them. And so they were on a mission to try to modernize their application. At the same time, Zappos is a subsidiary of Amazon.com. So while we were doing this modernization of their website, we were actually moving a lot of that stuff over to the Amazon.com e-commerce platform. So Amazon at this point had EC2, which was their public cloud stuff, but they also had their own internal cloud that ran their e-commerce platform. They were trying to move all that stuff over to EC2. I don't know where that is right now, but so I got a lot of practical experience in a really mature, what people call web ops or internet unicorn type shop, working with DevOps tools, the tools that they had. They were all custom tools. The cloud environment, the cloud infrastructure, all of that was highly custom. And I try to work with Red Hat's customers in North America and help them understand, what does microservices mean for them? What does this agility and digital transformation, all this stuff, mean to them? Because if you look at Amazon and Zappos, and you look at Netflix as the poster child for this movement, they're different. They shared some of the same founding principles for how they evolved and how they got to where they are in terms of their technology, but they're not exactly the same. They're quite different. So each of your organizations, by definition, is different and will be taking possibly a different approach. The principles can be the same, the founding principles are the same, but the actual implementation, how you get there, will necessarily be different. Okay, so I'm going to start off with the what, why, and when. I know we've been talking about this for, like I said, 3 years, but we haven't talked as much about the when. So let me lead into what the what and the why, and then let's get to the when to do it, because I've heard people say that when they're starting new initiatives, they're doing it as microservices. Okay, but I've also heard people say, well, microservices isn't the solution for everything. But then I haven't seen too much discussion on, okay, when is it not the solution for everything? Because it seems like it is. We're talking about it as the magic bullet, but we'll get into that. So let's start off with a quick definition. This is the ThoughtWorks or the Martin Fowler definition. Everyone's definition is kind of similar, and we talk about breaking up a large system. So I guess that's the first hint. We're breaking up a large system into smaller pieces so that we can change them independently of each other and some of the other qualities like fully automated deployments and DevOps and that kind of stuff come into the picture. These things all kind of intersect. And we hear a lot about the benefits of doing this. So if we're, if we have self-contained and single-purpose, we hear this quite often, single-purpose services, then they're easier to test, they're easier to understand in isolation, easier to change, because now when we do a deployment, we can deploy that one component, and we don't have to. Otherwise, if it's a big monolithic system, then you change one line of code, then you kind of have to redeploy the whole thing, right? So we have a little bit more granular change patterns that we can do. Scalability, so we hear this quite frequently as well. And scalability, not just in terms of the technology, but also in terms of the teams. So if you have gigantic teams trying to coordinate across all the teams, trying to coordinate across different silos of teams, the DBAs, the QA folks, the security folks, all of this becomes pretty challenging and becomes complex and slows you down. Now, these are supposedly, these are the benefits, but I would argue in some cases that some of these are not actually true. I would argue that breaking things down into smaller pieces, one of the things, let's see if my laser pointer works. Yeah, does that work on both sides? Yeah. One of these things, isolated and resilient to faults. If we break things down into smaller pieces, we can isolate the fault zones. We can also isolate where things fail. If one part fails, that's okay, because the rest of the application is still up. But in reality, when pieces start failing, that has the potential to cause a cascading effect, and actually has the you have the possibility of jumping those failure planes, those isolation zones, and affecting everything, which is the opposite of what we're trying to do. So we have some of these things. The testing part, yeah, we can test a single service individually, but testing a business flow, testing a business transaction, testing a scenario that touches multiple services, that becomes really hard. So there are drawbacks, and if we're going to be honest with each other about an architectural approach, then we have to call out the drawbacks. There absolutely is more complexity in the system, more unknowns. We can't say for certain. There's a lot of uncertainty in the system. Testing, like I said, becomes harder. Operationally, there's a lot more moving pieces. How do you do deployments? Resource overhead, network overhead, the lack of tooling, this type of stuff. Now, these are the areas where I think, at Red Hat, we're trying to help and we're trying to solve some of these drawbacks to enable you to be successful with a microservices architecture, but we can't just gloss over this fact. So why would one want to do this? We started off in the definition, we said, well, it's for breaking up large monolithic systems that were difficult to change, right? So some of the pain that we might feel. And as developers, architects, even the business folks, they know that making these changes can be painful sometimes. This is not meant for me I'm not going to read all this stuff. You guys can read it. But, it typically happens after a code base has been maintained for years, different developers, different requirements that have come in. We've monkey patched the requirements to just get it done quickly. So we've built up lots and lots of technical debt. And we end up with this type of experience when we try to make changes to the application. All right. When we talk about doing microservices, we are trying to optimize our architecture and the way we work for speed. And I don't mean performance per se, like cycles, optimize cycles, which that's a different conversation. But what we're optimizing is for the ability to make changes, to quickly make changes. And why might we want to do that? I said earlier on the panel that the business driver for adopting a cloud native architecture like microservices or things like DevOps, cloud in general, is to businesses have to constantly reinvent themselves. They have to constantly find new ways of entering the market and providing value to their customers. Otherwise, they're just going to, I mean, there's no invincibility. Every company is going to experience this, or they'll get disrupted. But so we want to take an experimental approach, a hypothesis approach. We want to innovate by trying to figure out what are the right questions to ask. But all the way down, even if we're not doing the innovation, we want to constantly and continuously improve the products that we have today, the flagship products that are making us a lot of money, making your organizations a lot of money and everything in between. So if the innovative stuff can go fast, which kind of by definition it should be able to, it's brand new stuff. You just churn it out and see what happens. But if the flagship stuff isn't able to continuously improve and open up new avenues for integration, like we've talked about, to enable new business lines and so on, then that's going to be a big problem. So we want to optimize for speed and speed of change of the system. But how many folks work in operations? Couple, handful. On the other hand, as operations folks probably will know, speed of change introduces or reduces reliability. That brings about pain when things start, bugs get introduced into the system, things start breaking, availability of core services goes down. So there's definitely a trade-off to be thinking about. But, and when I get to the next slides, we'll see that high-performing teams don't make that trade-off. So do we do microservices all the way down? And the answer to me, in my mind, is no. This is kind of a busy slide, and I'm gonna try to frame this as a metaphor that was first introduced by Simon Wardley. Does anybody know who Simon Wardley is? No, he's a strategist or thinker, in terms of technology and business strategy and so on. But he came up with this framing of how to describe the evolution of technology. You end up with great new innovations, and then they go, kind of like the innovation adoption curve. Great new innovations, they're differentiators, then everybody starts doing it, and then they finally just become utility. Everybody has it. Computer, I guess, would be a great example, right? Now you can just go to the cloud and get utility computing. But in terms of an organization, in terms of IT projects, and in terms of what the appropriate architecture for the type of project or the type of problem we're trying to solve, we can apply the same sort of thinking. And the metaphor is the pioneers are the folks who are out well ahead of 3 years ahead of everybody, trying to figure out what is going to be the next business, how we're gonna provide value. And you know what? That area is just packed with unknowns, unpredictability, unknowns. Right? We have no idea. We have to figure out what are the right questions to ask. So they're constantly experimenting. What does IoT mean? What does Kafka and Lambda mean? What do all these things mean to our business? What does big data really mean? Asking questions, putting things out in front of customers, and getting feedback and learning from that. The town planners on the far right-hand side of the slide, they're the ones that are tasked with how do we make the existing flagship products more optimized, more efficient? How do we drive down the cost of that, get more money out of that? The way they think about management and approach to architecture and so on is totally different than what the pioneers are dealing with. Now, in the middle, the settlers they're the ones that are taking from the pioneers. If the pioneers find something interesting, there might be some value here. We find maybe a product market fit and possibly a new market, emerging market. Then the settlers take that from the pioneers and they grow it. They build sales teams around it. They build product teams around it. And this becomes the emerging technology that could one day, be the next flagship product for the business. Now, if we start thinking about it in terms of that, where does software architecture fit into this model? And this isn't a foreign thing. We see companies, this is from Intuit, who align their IT portfolio investment strategies according to these three different categories, where the exploration phase they get about 10% of the expenses and projects. The growth stage is about 30%, and then their existing business is about 60%. What's interesting is their exploration ideas. One of these ideas that came out that seems kind of interesting was called snap tax, and I hadn't heard of it until I saw it in a blog. So what they did was they came up with this crazy idea. We're just going to take our phones and take a picture of our tax returns and just have them automatically filed. And that's mind-blowing. But for some scenarios, that tends to work out. And just a crazy idea that they came up with that customers found a lot of value. And now it's got like lots of good ratings in the App Store and so on. And now the way that I try to explain this is that so we said microservices is an optimization for speed. The key word there is optimization, which means we're making trade-offs. And we're trying to achieve something. In the pioneers phase, like I said, we're dealing with a lot of unknowns. We're creating as many cheap experiments as we can to reduce uncertainty and learn about what problems we might be able to provide value with. The way we implement those, maybe we'll implement that with code, with applications, with software. We might create an MVP. How many people are working on projects that are labeled MVP? A couple. These are the exploratory phases. In my mind, if you're doing this to ask questions to your customer and change it as quickly as you can, it makes more sense to have things co-located than it does to distribute everything out. What are the APIs? Who knows? What are the boundaries? I don't know. This is not an established market. We have no idea. So why would you invest all the time in creating this complex architecture when, number one, you're probably just going to end up throwing the MVP away, or number two, it's going to change so that distributing it out and coming up with APIs and boundaries like that too prematurely is going to slow you down. Now, like I said, that's just maybe 10% of the business strategy exploration. But as we go down into maybe the settlers realm, where they're actually trying to build out a product, they've found a product market fit. They have a better understanding of what the business behind it would be. Now that starts to, depending on how big the team gets and the complexity of the app that you're trying to build, the scale that it needs to. It could be perfectly okay to co-locate components, or you can start to move to a distributed microservices style architecture. Now in the town planners area, and this is where the Netflix, this is where the Zappos, this is where the Amazons were facing trouble. They found something that provided market value. They grew it to the point that it was kind of now difficult to grow, and they started to feel that pain. And then they started going toward the microservices architecture. They were able to understand where to draw the API boundaries, where and how to change or organize the teams around capabilities and so on. Now, this is just a guideline. This is just hey, not everything is a microservices architecture. Don't over-optimize or prematurely optimize when you don't need to. And still the bottom line is, in each one of these phases, we want to go fast. We want to go fast. And we want to be, the stuff we deliver to production, we want it to be reliable. So those, regardless of whether it's microservices or monoliths or co-location or mini-liths or whatever, that's still the goal. So in my mind, don't over-optimize or don't prematurely optimize if you're building MVP tests that are probably going to be thrown away. You're building very simple applications. Your application is a packaged software. I don't know how many of that, to whom it applies, but if you're going to be packaging software and delivering it, you don't want 100 moving pieces, so you co-locate them. Now, regardless of which pioneers, settler, or town planner and type project we think we are, we want to make it economical to make changes fast, to make small changes very fast and very reliable. And this is what Gene Kim calls high-performing IT. A high-performing IT organization is one that, so I guess this is, I think, from one of the State of DevOps reports. they characterize a high-performing IT as being able to do 30 times more deployments than their peers, which turns out to be a few times a day, with a 50% lower change failure rate. So we're able to improve our stability and improve our ability to ask questions. Basically, each one of these deployments is a way to ask questions about whether or not this idea we had, the requirements we had, was even a positive influence on the outcomes that we were expecting. High-performing IT teams, and this starts to bleed into sort of the cultural aspects, because you may or may not find this in your organization. Encourage to experiment, or encourage to learn from failure. You've heard the phrase, fail fast, right? It's not about failing fast, it's about learning fast. You might characterize it as a failure, but you've hopefully learned something from them. Working in small batches, delivering to production many times a week, and so on. So these are some of the characteristics of high-performing teams. But they need capabilities and the processes and practices to be able to do that. They need things like continuous integration, continuous delivery, automated testing, reliable and safe ways to bring applications and changes into production and maybe back them out, on-demand self-service infrastructure, and so on. You can read it. But these are the capabilities that, if you look back at the Amazons, at the Netflixes, and the Facebooks, and so on, they built all this stuff. They built this by hand. Like I said, I was at Zappos in 2012. We had this stuff. They invested a tremendous amount of money to do that because they needed it. And that subsequently made these changes to the system cheaper. These experiments to run cheaper. And then so cloud native in my mind is, how do we make this stuff, from the applications to the platforms to the processes to the culture, how do we make it economical to be able to move fast like this, regardless of the IT project phase that we're in? Netflix, for example, built their platform on top of Amazon EC2 or some of those components from Amazon. And they targeted a JVM runtime, because that's what you're using, Scala and the JVM and so on. And they found very quickly that when you build a services-style architecture to scale for what they were trying to do in an elastic and unpredictable environment like a cloud, there are certain things that you have to solve for. Distributed configuration, service discovery, load balancing. Who's heard of the Netflix OSS stack, the JVM stack? Just a handful? Just a couple? Come on, guys, be active. Come on, who's heard of it? All right. Now, what's interesting is Netflix started open sourcing some of that stuff. Facebook has always kind of been, we'll throw stuff over the fence and see what happens. But Google was on, when Docker hit and containers as a deployment mechanism, as an application packaging mechanism was starting to become a thing, Google was working on a next generation version of their cluster management solution that they were thinking about open sourcing. And it just so happens that Red Hat also had a container management solution that we were working on a third iteration of as well, to take advantage of some of the things that the Docker community was doing. And they came together and said, well, hey, Red Hat, you know open source in the enterprise, and we're Google, so we're, we know scale and containers, so why don't we work together on this and bring it to open source? And it's just kind of interesting now that we started off there, when at the time, the container PaaSes, or the platforms at the time that were emerging, that were looking to become successful, were the Cloud Foundries, the Mesospheres, the Docker folks, and today, through the community and the power that Kubernetes brings to these types of problems, Kubernetes has kind of won that battle, that show. Even though all of them came from a Google heritage, the Cloud Foundry folks, Mesosphere folks, they all came from a Google background. They thought, well, I'm going to go off and I'm going to build this thing, kind of looks like Borg. And Google came out and said, well, we're just going to build our own thing that we know we built, and we'll do it again. But more importantly, adopted, brought in the community and brought in extra other partners like us and CoreOS, and now there's people at IBM, Microsoft. Everybody is committed to it. And so Kubernetes is the standard way to go forward, and has become the API for cloud workloads, whether on-prem or in the public cloud. So Kubernetes, which is also a great foundation for managing workloads, managing containers, is part of the solution. When you actually try to use it in an enterprise environment or any environment, you're going to need things like, well, you got to set up the networking. That's kind of complicated. Or we need to build container images, Docker images. And we're not going to expect every developer to have Docker on their machine. And we're certainly not going to accept Docker images from any random machine. So we need some way to organize the building of these applications. We need some of that infrastructure. And so OpenShift at Red Hat is our distribution of Kubernetes. And we support Kubernetes through OpenShift. And when Red Hat says they support it, they mean we have a lot of committers. We're the second leading contributor to Kubernetes behind Google. And so we're all in, and we have been all in since the beginning on Kubernetes. But we've built all these things out because we work with the enterprises. We know security is a huge concern. We've led the security and the networking working groups in the Kubernetes community and so on. Building CI/CD pipelines with the full, how do we do the container build, how do we do testing, how do we do scanning, vulnerability scanning, all this stuff. These are things that we've thought through, and another thing is we work with, I don't know how many are public. I think it's 60 or so that we are public, but there's a lot more that are not public. 60 different organizations that are deploying and running containers in production today, and each one of those deployments is slightly different. There's one particular type of security concern over here. There's one particular kind of way they want to do builds and deployments over here. And so we have way more operational experience than anybody at all, even Google, running Kubernetes. Google's really good at running Kubernetes in GKE. That's their one place. But Red Hat is really good at running Kubernetes in the enterprise. Okay. Now, once we start building apps and bringing them into this container environment and deploying them, right? So we can build continuous delivery and deployment strategies into the container, into the cluster here on top of Kubernetes. We know we're using containers and container images to allow us to move applications from one environment into the other very safely and so on. But once these services start coming up, they need to communicate with each other, right? We talked about this a lot today. They expose APIs. They need to consume APIs. They need to integrate with back-end systems, existing systems, maybe monoliths, or partners. There's going to be a lot, and then of course the microservices themselves. If you're going to build out an architecture like this, there's going to be a lot of components that need to communicate and talk. Now, the problem with that is we're going to have to do this over the network. Networks in general are pretty. I'm sure if you're developers and architects have heard or seen the fallacies of distributed computing. One of them is that the network is reliable. It's not. We need a way to interact with these services, which in the past were just maybe co-located and they were just talking in the same memory space, right? And they could just make a call and the call would return. And now we're moving this into an environment where there can be lots of different programming languages used to implement various different services, and these services have to communicate over the network. We can solve integration challenges and business level concerns inside the services themselves, like we talked about earlier. But what do we do? What do we do at that network level? It feels like at the network level, things like, there might be, you'll want to implement timeouts. You don't want to just make a call and then sit there and hang, right? Because then that uses up resources, that uses up thread resources and so on. Things like circuit breaking and retrying, these types of things that applications, we have to build that resiliency in to the applications. Things like, so because when we make changes to the system and things start to go sideways, we don't want cascading failures, right? We want to contain them. The second thing is when we do deployments. When we do deployments, how do we do safe deployments? There's actually a difference between doing a deployment and a release. A deployment brings code into production. A release actually brings traffic to the deployment. So how can we do this in a safe way that we can get deployments into production and maybe give them a little bit of traffic, not all of it, or give them shadow traffic. We'll just siphon off some of the traffic and give it to this new release and see how it behaves, right? So a little bit more complex and mature deployment and release strategies. How do we do all that stuff? And then, of course, we can't understand what's happening and what are the impacts of a change without having logging, metrics collection, metrics at the infrastructure level, at the application level, things like distributed tracing to understand what services are talking with each other and how long are they taking and why are some of them failing, why are some of them slow. We need a way to observe and come to an understanding about what's happening in the environment. In the past, we solved things like service discovery, load balancing, retries with technology like message queues. How many people have done request reply over message queues? A handful. Now, the idea was how do we build that sort of functionality into the system? And we also thought, well, if we get all the traffic going over these message queues, then we can control it. We can see it, we can control it. And so that sort of stuff didn't pan out as well as we thought. But then we continued to think, well, we also need transformation and orchestration and adapter mediation, that kind of stuff. Well, we'll just layer that on top of the messaging queue. We're already doing RPC over that. Well, let's just do some more stuff on top of it. What that ended up becoming was a bottleneck for a handful of different reasons, like we've talked about today, and we've also talked about how this sort of centralized way of doing integration is not appropriate for a cloud-like distributed environment. But the biggest problem of this was we were jamming too much business logic and too much business concern. We were spreading that out over multiple teams. And this one centralized team was becoming overloaded, and they weren't able to keep up with request changes, or the changes that they made were breaking everything else. Well, so then we decided, okay, we'll just do REST. We'll just do HTTP. We'll just do APIs. We don't need integration anymore, right? And that didn't pan out either, because when you start making calls over the network, you still have those challenges. So now, okay, we got rid of the ESB, and we got rid of the message queues, but we still have those challenges. We need to solve for that. Also, along with at the same time came the advent of APIs as products, and how do we build public-facing APIs? How do we handle security? How do we handle rate limiting? How do we handle quotas and that kind of stuff? And that's where API management started to come in to solve some of those problems initially. And then we thought, well, we got all the traffic going through this API management thing. Well, why don't we just add transformation and orchestration and mediation into this? And that's not a good idea. That's a terrible idea. That is just going to recreate your ESB in new technology. How did Netflix handle this? Or maybe some of the internet companies, they didn't use ESBs. If you're familiar with the Netflix OSS stack, things like Netflix Hystrix is a library to implement circuit breaking. So if you make a call to a network resource and it doesn't return in time or it fails, then we'll stop. We'll open, quote unquote, open the circuit. So we'll shed load. Anybody else that tries to make that call, we're gonna stop it, because we don't want to overload the system with failed calls. If it's a database, let's say, that's slow, we don't want to just keep hammering it, right? They came up with things like the Zool Edge Router, which allowed them to do these safer deployments, bring new pieces of code, changes of code into production, and be very surgical about what traffic actually went to the deployment as part of a release. And Ribbon for doing client-side load balancing, Eureka for service discovery, and so on. So they had this pile of libraries that they open source. And people started to adopt it. But I want to remind you that this technology was written 2009, 2010, and was written at a time when VMs, so Netflix was deploying immutable VMs in their CI/CD pipeline, and they're built around Amazon EC2. Things have changed a little bit in the container world. If we look at some of the derivatives, oh, that's not the slide I was expecting. Well, okay, so there's an illustration, right? So we took those concerns, and I would argue that those are very much networking concerns, application level networking concerns. Things like retries, timeouts, circuit breaking, distributed tracing, metrics collection, quota, rate limiting, this kind of things. These are not application-specific things. Every application needs this stuff. And you can kind of draw the parallel between, well, we didn't make everybody write their own TCP libraries and inject those into their applications, right? We pushed that down into the operating system, let them handle it. But in many ways, we're treating some of these same networking concerns by just jamming them into the application. Now, of course, if you're using some derivatives of the the Netflix OSS stack, like a Spring Cloud, or the Netflix stuff directly, that'll be fine if you're a Java developer and you're deploying onto JVM, or if you're using Spring. But if you're using something else, like Vertex, anybody heard of Vertex? Raise your hand if you could. Just a handful. Or things like Wildfly or EAP, or any container, any Java container. You're going to have to figure out a way to reuse or shoehorn that stuff into your application. But what if you're using Node.js or Go or Python? So any of these different frameworks or any of these different languages, you still need to have this functionality. Now you can go off and rewrite it, or you find a library that might implement it. Now you have to maintain and keep up to date all of the different variants, all the different flavors of this implementation, and hope and pray everybody uses it correctly and that it's correctly and exactly the same, implemented exactly the same across all the different frameworks and languages. That's a pretty tall order. Things you must solve for. All these things, right? There's lots of stuff. All in the name of get deployments out fast, get them out safely. And if there's problems, we want to build a system that's able to handle problems and hopefully roll back or roll forward. Now, let me introduce you to a piece of technology called Envoy. Has anybody heard of the Envoy proxy? One. Okay. Two. Okay. So now this might be a pretty bold prediction, but just like Kubernetes and the community that's come around Kubernetes has kind of catapulted that to the sort of the leader, the vanguard of workloads across different clouds and cluster management. We're going to see technology like this start to influence how we implement some of these concerns and probably get to the head of its class as well. Envoy is a small. I don't want to use the word lightweight because everybody uses that word to describe whatever the new greatest thing is, but it's a small proxy, service proxy, written in C++. And the idea with Envoy is that services talk to the proxy, and then the proxy talks to the outside network. So if we look here, our application talks directly to a proxy, and then the proxy communicates with the outside world. And it can then intercept and basically wrap those calls with the functionality that we need. Now, the interesting thing about Kubernetes is in the Kubernetes deployment model, we can group containers atomically. We can say that these two containers have deployment affinity. They have to be deployed. They have to be co-deployed, always together like that. So we can inject these proxies, these service proxies, directly next to our application instances as a sidecar, is what we're calling it, that the application doesn't even need to know about the proxy. The application just talks to the network, but the proxy is actually doing the mediation for it. Right, and on the other end, it's true too, like the call is coming into a proxy and then to the application. And we're able to instrument and add this layer of resiliency and control into our applications, regardless of the programming language, regardless of the framework. And when we keep it up to date, we can say for sure that it's correctly implemented the way we expect it. Now, I said it was written in C++ for a reason. Not only performance is a huge thing, overhead is a huge thing, but the more important thing is under load, we don't want our infrastructure getting in our way. We want a predictable response times and predictable behavior under load. We want very predictable tail latencies when we get to the 99.999% percentile when we start taking load. And writing it in C++ was very strategic to be able to accomplish that. The other ones, if you write it in a JVM or a garbage collected language, who knows what happens at those higher ends of your traffic load. So if all of our service instances have these proxies, we can do interesting things. Not only do we get circuit breaking, retries, timeouts, that kind of stuff kind of built in, but we also get control point across the cluster, across the mesh, that we can control service discovery, we can control traffic routing, kind of the same stuff that we were trying to do with the message queue. And there's a project that has emerged that will, just like Kubernetes and others, will be joining the CNCF hopefully at some point, called Istio, I-S-T-I-O. Istio is the control components, the control plane for being able to manage a cluster where the applications have this little service proxy. So we're able to add configurations. We're able to change routing policies. So for example, if I deploy version 2 of my app and I want to do a canary release and I want to just have a certain small percentage of live traffic coming to it, I can control that from Istio. I can get things back from these data proxies, or the data plane, the service proxies. I can get things back like distributed tracing. So if all the calls are going through these little control points, we know exactly how long calls are taking, where circuit breaking is happening, where 503s are happening, where to inject tracing metadata. So we're able to pull things back into a distributed tracing system like a Zipkin or a open tracing system like Jaeger. Does that make sense? Are there any questions? I'm going to show you a quick demo. Yeah.
So the question would be, where is this going to fit in with Rescale?
Exactly. That's a great question. So there is overlap between what's traditionally been the API management layer that provides security, authentication, rate limiting, quotas, grouping of requests, and so on. Now, because we're talking about doing that same thing between the services. So typically, the API management has been used for the north-south, the ingress traffic. Doesn't have to be, but that's kind of typical. Istio is addressing the east-west traffic, internal traffic. But that bleed over does allow, at least in my mind, us to use or set policies in the API management layer for north-south traffic or east-west traffic, and have the enforcement of that at the ingress layer as well as in between in the east-west. Right. So there's still a lot of moving pieces here, but this is the direction that we're going as well. So like I said, this is still upstream and community stuff. It's not production ready yet. I'm telling you about it because this is the direction that the community is going in. This is the direction that we at Red Hat are going in, and absolutely will, those overlapping concerns, we're going to try to make those work really nicely. Okay, let me try to do the demo real quick. I only got 5 minutes, but let's see how it goes. Okay, so what I'm going to show here is I can get traffic coming in to an application that will be implemented with microservices, let's say, right? So we have our product page service that will be calling into the reviews service. Right here I have 3 different deployments of the reviews service, okay? Remember I said deployments, not release. So we have 3 different deployments, and then the review service is going to call back into the rating service to get, to enrich it with additional data like the ratings. Now, when I come over here and I look at my app, this is the stock book info demo from istio.io. So purposely doing that so you can go and you can recreate this for yourself. And I'm running this on top of the latest build of OpenShift from the OpenShift open source community origin. So cross your fingers for me. Okay, so here we go. So I'm at the app. It's pretty simple. If I refresh it, if I start refreshing it, I'm going to see off to the right-hand side 3 different versions of the review service. Okay. Right now, there's no routing rules. So in a Kubernetes world, an OpenShift world, it'll just load balance across all of those versions, which we don't want right now, right? So if I refresh it, it'll bounce back and forth between the different versions. If I come over here, and you may or may not be able to see this too well in the back, but I'll explain what I'm doing. We're going to set up so we don't have any routing rules right now. If I do an istio control get route rule, I don't know, let's see, does this work? Yeah. No resources found. Now, what we want to do is route all traffic to V1, version 1 of the services. This is what the routing rules would look like. And if I find the routing rule for the review service, reviews, what we're saying is anytime anybody wants to talk to the review service, force it to version 1. Force all traffic to version 1 of the review service. So let's do that. We'll do the create route rules. Those were created. Now if I go to the page here and do a refresh, I shouldn't see black stars, I shouldn't see red stars, I should just see version 1, which is the one with no stars. Okay? I refresh a couple times. Okay, looks fine. Now let's come back here. If we list, so we can list the routing rules. Istio is a layer on top of Kubernetes, so we're actually using native or OpenShift in this case, but I'll use those terms interchangeably. But all of the configs, all that stuff live inside of OpenShift as a layer on top of Kubernetes. So let's do something. Okay, I'm getting. This is what the routing rules look like. Don't worry about this stuff. We're going to do the next thing we want to do is deploy a version 2 of our service. When we do that, we don't want to replace version 1 completely. We want to slowly release version 2, and maybe we have a specific group of people that we want to release it to. Maybe we just want to release it to our internal users. Or maybe, let's say, another group could be a non-paying user type thing. So what we want to do is we want to implement we're going to slowly bleed traffic over in a very controlled and reliable way. Yep. In this rule, what we're saying here is for users that are logged in, whose username is Jason, and this is we're matching on headers, we could match on other things, then route that request to version 2. Right? And now this isn't the traffic that's coming in. The traffic coming in is hitting the product page service. But the hops that it takes after that, and in between the cluster, the east-west traffic, is what we're controlling here. So if I make that change, and come back to my service, if I refresh it, I'm still on version 1, which is what we expect. If I click sign in as Jason, now I'm routed to version 2 of the service. Right, so we have very surgical control and routing over the traffic that's happening inside of the cluster. So we're running out of time. One of the other things I want to show you is when we have these control points, when we have this data plane, we can pull metrics back about what's happening, what requests are failing, what are not. And we can dump that into Prometheus or any metric collection system, and we can see what's happening live to our traffic in the system. We also get things like distributed tracing because all of these control points, we're able to inject all this stuff. So we're able to see the different spans for the calls being made across the service. We didn't add this stuff as application level libraries into each of the applications. This is purely because of the service proxy. Okay, so I'm out of time. That's, I do want to point you to a couple of blogs that I've done about this sort of topics. If you go to developers.redhat.com/blog, you'll be able to find that material. Reach out to me if you have any other questions. I'll be here for a little bit afterward. Thank you so much for coming and listening. Thanks.